Hi everyone, welcome to this webinar on machine learning and MFG games. Today we are very happy to have Bruno Ziliotto from Paris, who is a CNRS researcher and a researcher at the Paris Dauphine University. So thanks a lot, Bruno, for accepting the invitation, and please feel free to start whenever you want.
Thank you very much, Mathieu. And hi, everyone. So the work I'm presenting today is a joint work with Eran Shmayak with Stony Brook University. And we basically in the paper introduce a model of Bayesian learning in MFG games. I will start with a small introduction to motivate the problem and emphasize some connections, and then I will describe the model, derive a system of PDE equations that characterize the equilibrium, and then talk about existence and uniqueness of this system. So in fact, Eran and I are relatively new in the MFG community, since it's our first work on the topic. And we are game theorists, and of course we have seen all the recent developments on the MFG games, and we thought it was quite interesting. And we have noticed also that many classic game theory concepts have been adapted to the MFG games. So, for instance, learning dynamics, when players don't know how to play and they start to implement some simple procedure, like for instance fictitious play, to learn how to play in the MFG game, or correlated equilibria, where players can coordinate on some public signals, or potential game, which are games with a special cost structure. All these ideas are rather old in game theory, but they were used recently in MFG game, and we thought that this interaction could be quite fruitful. And one topic that we investigated particularly was the topic of incomplete information. So, in fact, in game theory, incomplete information is everywhere in the literature, because of course agents that take decisions, they may not observe their environment. They may observe public signals, private signals about it. They may or not observe the actions of the other players. And so incomplete information leads to many different models, and it has been widely studied in game theory. But what we noticed is that it has not been so much considered actually in MFG games. So the idea of the paper was to develop let's say a simple MFG game model with incomplete information. Of course, there are many ways to model and incomplete information. So this is just one contribution about it, and we hope that it's interesting for the MFG game community. Just a few words about literature. So I mentioned before the topic about learning dynamics, where basically you think about agent as being not necessarily super rational or super able to compute everything, like it's mostly the case in real life. And you ask yourself whether there is a simple way to learn through repetition how to play well. So, for instance, there is a paper by Cardage and Annie Canlo about this topic, about fictitious play. But this is not what we would call incomplete information, because here it's more the agents don't know how to play and then learn how to play. Whereas for us, incomplete information would be more players are rational. They know exactly the description of the game, but there are some parameters that they do not observe. So this is what we mean by incomplete information. So two related papers are the one of a recent one by Bertucci, where they study a MFG game system where players do not know the initial distributions of players. So this is one of the first work, I think, on incomplete information. And another one is so from from 2023, is a model where you have an unknown state that only one player observes. So there is a player that is like, let's say, big, a major player, and he knows the state, and the other ones are like in the midfield game classic model. They are small players. They don't know what is the state, but they observe the same signal about it, and then the play goes on. So these are maybe the closest paper to ours, and it's also interesting to notice that it's well related to classic models in game theory, like the Oman Mashler paper from the 60s, and I'm sure that continuing in this direction will be very fruitful. So what do? We start from the classic Lasry-Alliance model, and we will add just one thing. It is that cost function will depend on some parameter that is fixed. So it is not time dependent. It is not action dependent. So we will call it the state, and it's not known to players. So they don't know the state, but they observe some stream of signals about it. So private signals, each small player has its own signal. And then they play the classic midfield game. They each has a position, and they have to choose their control. And they observe their position and the private signals. And what we will do about it is to derive some new midfield game system and prove existence and uniqueness under some condition of the midfield game system. So this was the general description of what we are going to do. Now let me go to the model. So as I said, there is some unknown state S, and we will actually be very specific about the distribution of this state in order that the model be tractable. So we assume that S is distributed according to a normal distribution of mean 0 and the variance 1. And the signaling process will be basically a Brownian motion with a drift, where the drift corresponds to the state. So you have an equation, dzt equal sdt plus sigma dbt, where sigma is the variance. And they all observe this one version of this equation. So each one has a Brownian motion. And then there is a position that is as usual. So it's driven according to an equation where each player chooses some control alpha, and then it's perturbed by a Brownian motion. And this Brownian motion is independent from the one that drives the information structure. So you can see the difference between the classic MFG model is this signaling process, and which equation is somehow similar to the one that drives the position of the player. But instead of having a control, you just have S, which is the unknown state. But the analogy between these two equations will be very useful to derive equations. As any questions so far, don't hesitate to interrupt me because I don't have so many slides. So if you have something that's clear, please tell me. Okay, so this is a model. Now, what is the objective of the agent? So the first important object is the density of the player position. So for each possible state, there will be, and for each possible time, there will be a density of players, so which is noted by rho s tx. The reason is that the players observe some information about the state, so the state influences the position of players. And so the objective of the agent is the following. So we assume that the game starts in time small t and terminates at time big T. And actually, I present what I'm gonna present today as a cost definition is simpler than in the paper we wrote to avoid too many notation. I will assume quadratic cost on the optimal control. So in the paper we have it's possible to have more general cost function, but let's do that for today. And the flow cost, the F, that depends on the repartition of player. So this one depends on S. So the cost, the control cost does not depend on S, but the flow cost depend on S. And you can see that the signal does not affect the cost. The signal only affects information of players. Okay, so this is the cost function, and just I think it's nice to have maybe some idea of applications that could be done with this kind of model. So first one what we first thought about was product differentiation. So imagine if you have that players are companies. So there is a continuum of companies. And they each produce the same type of product, like for instance a cell phone, and then but they can produce, they can have there can be different characteristics of the product, and so the position of players could be the characteristic of the product, and they can change, they can move the characteristic according to research and development. And then what is the state? It can be the preference of consumers. Maybe at this time, at the time of the production, consumers prefer cheap phones, or they prefer phones with this type of characteristic or this type of screen. And this state is not entirely observed. It's discovered along the path. Another example is portfolio management. So imagine now that players are investors, and so their position is basically the composition of their asset portfolio. And then the state that is not known can represent the quality of their portfolio. And this, of course, they may not know it. They will discover it through the observation of the performance of this portfolio. So this is just two types of examples that can be done. But actually, in some sense, the situation where there is incomplete information in application is much more common than the case where there is complete information. So it's not very difficult to find examples. Any questions?
So sorry to interrupt you. Is it possible to show again the previous slide, please?
Yeah.
So in this one, okay, so here S is completely fixed. It influences the drift of Z. And okay, would it be possible to take S depending on time, or in your context, it doesn't make sense? Like you really want the state to be.
No, I think it could definitely. I mean, basically, we try to write maybe one of the simplest and complete information model, and make it tractable. I think that, there would be no problem in making it state dependent.
Okay.
Yeah.
Okay.
Sorry, time dependent.
I have a question. Sorry. In the example with the portfolio, could you please? I just missed it. There was a slide before. So where is the portfolio here? And what
I mean, it's like you buy different types of actions, for instance, of assets.
Yes. Yes. So F is the value of the portfolio. F capital.
Okay, so for this example, I think it makes a bit more sense to okay, so thank you for the question. Actually, something that I forgot to mention. You can see here that there is no terminal cost on this payoff. But again, this is only because I didn't want to have too many notations for my talk. But you can definitely add some terminal cost. And I think for the portfolio management example, it makes maybe more sense to assume that there is a terminal cost. And then it would be like you you choose the composition of your wallet, and then at the end of the game you get a return cost on that depends on the composition of your wallet at the last time. And,
okay.
and I think
And
does it answer our question?
Alpha?
Or, yeah.
And what would be the alpha then in this case? Alpha. Was it alpha? Mm-hmm.
I mean, it's like you have your wallet and you move it in a continuous way according to the information you have on the quality of the portfolio of the assets you are buying.
Okay. Thank you. Thank you.
Again, I'm not pretending that this is a truthful representation of reality. It was just to give some insight of what could be an application. Of course, if you wanted to really to study precisely this application, you would probably need to modify a bit the model, but or maybe a lot. It's a theoretical contribution that puts the basis of an incomplete information model, and then it's I don't pretend to do a precise application with. So something that is crucial and actually that justifies the title of the talk, Bayesian learning in midfield games, is that, so basically what is going to happen is that the relevant variable is, in terms of information, is the belief of players about the state. They observe a stream of private signals and they deduce a priority distribution on the possible states. But in our framework, because we take a signaling structure that is so particular, that is formed with normal laws, in fact, the law of S conditional on the stream of signals is extremely simple to describe. It's described by the following equation. It's actually a normal distribution that its mean that only depends on the last signal. So in fact, all your information is encapsulated in the last signal that you receive. And then you have explicit equation for this mean that we did not buy, RT of Z, and the variance sigma T square. You can observe that as T goes to infinity, the variance goes to 0, which is consistent because when time is very long, you will get to learn the state. So it's a very crucial property that will allow us to derive tractable equations that live in a finite dimensional space. So to summarize, given all the past signals, my belief about S only depend on T and my last signal ZT. So ZT is a sufficient statistics for all the information I get. And so it will allow us to describe the situation of each player by, in terms of information, by just his current signal Z, and of course we need the current position. So at the end, the midfield game system that we will write will be somehow a midfield game where there is an extended space variable that encapsulates both the position and the current signals. So now let me move to the definition of an equilibrium. So given some initial player density, so sorry, one thing that I should have emphasized is that, again, for simplification purpose, I will assume that the position lies in the torus, like it is most often the case in theory papers in midfield games. You can do it in RD up to more technical statements. So I will take some initial player density. And for each possible state S, I will have this function ms that take as variable the time, the position of the player, its current signals, and that describes the density of players in this space TD times R. So there is a space, a product space, position signal that describes the state of the players at each time t and given some state s. So compared to standard mini-field games, the novelty is that there is a state S, and there is also a variable Z that represents the current information of players. And we say that this collection of mappings MS is an equilibrium if there exists some control alpha, such that alpha is the minimizer of the control problem I mentioned in the previous slides. So I record it there, where you have a quadratic cost in your control and flow costs that depend on your state, on your position, and on the position distribution of players. And moreover, given any state and any t, the distribution of the couple position signal when everyone plays alpha is exactly this MS. So this is, again, a generalization of the standard MFG equilibrium condition. And then the question is, okay, so we have this notion of equilibrium that will be like the outcome solution of rational players. Can we describe it by a system of PDE equation as we do in the standard case? Sorry, I think there are some messages on the chat, but I don't know. Okay, this is.
Oh, it's okay. Yeah, there was one question about the link.
Yeah, okay.
And I have one quick question here, sorry, if I may. So in this case, MS, okay, so it's defined over 0t, td, and r. At time 0, for any state S, it should be equal to m0, or...
Yeah,
okay. And the third
you
variable?
need to have some initial solution.
Yeah, I see. And the third input in MS is S, right? The real variable. So you have time, you have
So
TD for the state.
again, I assume again, I assume that the signal is real, but you can do it in any finite dimension.
Okay, sounds good. And here, all the players kind of know that the initial distribution is M0, right? So in this case, the initial distribution is known from everyone, but they don't know the state. Okay.
Yeah.
Okay, thanks.
And okay, so let me derive the MFG system. So let me just recall how it works in the standard case where there is no unknown state. So I mean, you probably all know this, but there is you can describe it by a couple of PD. So Hamilton-Jacobi equations that describe the solution of the optimal control problem of the players, and the Fokker-Planck equations that describe the evolutions of the measure of the players when they use some control that is minus x derivative of u, which correspond to the optimal control in the Hamilton-Jacobi equation. So this is what I wrote here. And now, so I'm gonna. So there will still be two equations, but I will emphasize what is new on the equations. So first, so yeah, let me first say that the main difference is that the flow cost depends on the state S, but players don't know the state S. So instead of having just the flow cost in the Hamilton-Jacobi equation, there will be the expectation of the flow cost with respect to the information that is, in the case of our model, the last signal Z. So that will be one of the first difference. And let me explicit this expected cost function. So I remind you that given the path signals, all the stream of path signals, the belief of S can be characterized by the normal law, where the mean are explicit function of Z, and the variance is a function of time. And then the expected cost function, I mean, is just the expectation of the flow cost when S is distributed according to the aforementioned normal. And OS, I recall that OS is a marginal of MS, meaning the position distribution of players, because again, what's important in the cost is not the signal, it is the position of players. The signals only influence the information of player. So this F tilde, this is what we will find in the Hamilton-Jacobi equation. And now you can see that even if the flow cost at first did not depend on time and on Z, now the F tilde, the expectation depend indeed on Z and on time. And I put just to make it clearer, I put in red the new terms in the MFG system. So M is so given M a distribution, M will be an equilibrium if it satisfies the coupled PD system, where the novelty is that now F is F tilde, so expected cost. And there is the term in the Hamilton-Jacobi equation, there is a term RT Z scalar dzu. And this term only appears because basically, if you, I mean, a good way to see it is that the form of the equation in Z is dzt equal sdt plus sigma dbt. So in some sense, you can, by analogy, say that S is a kind of fixed control that is independent on X, Z, and T. And therefore, when you put it into the Hamiltonian, you will the term that is associated to this to the derivative with respect to Z will just go out of the Hamiltonian, and you will just have this term S dzu, but then you integrate with respect to S, and you obtain this term. As the Fokker-Planck equation, it's a bit different because it's a collection of Fokker-Planck equation. Basically, given any S, I have some Fokker-Planck equations that depend on S. And again, the novelty is, I mean, the term you have a divergence term that depends on S. Again, you can view it by analogy with between the equation of dxt and dzt. Before there was the dxu in the divergence come from control alpha. So if instead of alpha you have S, then you just put an S. And you also have the Laplacian with respect to Z. But yeah, formally it's rather easy to derive. But conceptually, you may wonder, okay, but is this a classical MFG system at the end? Can we say that it's an MFG system on an extended space XZ position signals? Not really, because the problem is that the second equation is a collection of Fokker-Planck equation. And we didn't find a nice way to transform it into a natural Fokker-Planck equation that would only depend on X and Z. So it's not a classical MFG system. And basically the idea is that there is a difference between the equation that drives the evolution of the players and the equations that the equation that drives the position of the player and the equations that drive the choice of the control. The choice of the control only depend on signal, because you only observe the signal, you don't observe the state. Whereas the distribution, the variable position signal is driven by an equation that depends on S because of the dzt equal sdt plus sigma dbt. So somehow this in the first equation, what is important is the expectation of S, and in the other equation, it's S itself. So that's why we don't manage somehow to put them together into a general system written on X, Z. So in particular, if we want to talk about existence as uniqueness, we will have to have we cannot just apply directly some results that exist for the classic MFG system. So a a first result that is more like a technical lemma, but that is very useful for both for existence and uniqueness result. Is the following: is the fact that okay, ms is a function of s, but actually it's a very particular function of s thanks to the special signaling structure that we put. Basically, ms, the lemma says that ms, the dependence of ms in s is can just be put as a product between this term phi and some functions that only depend on t, x, and z, so not on s. And this phi is just the distribution of it's just the density of the normal law of mean st and variance sigma square t. So the interpretation is the following. It's basically, it says that everything is as if I mean the way you can describe ms is first you fix some state s, you draw z according to its distribution, which is a normal law st sigma square t. This phi is actually exactly the law of the signal at time t, given signal s. And then given z, you have some functions that where s does not appear. And this is this product structure will be very helpful for the following. And then tau is just the solution of another Fock-Planck equation, but where s does not appear. So this will be, for instance, useful in terms of existence result, because then you get very easily regularity in terms of s. And we will see that it will be also a determinant in proving uniqueness of the solution. So the first results, I will not describe too much the proof, because it's not so different. I mean, there are some technicalities, but it's not so different from the standard case. So the first result says that indeed there exists some equilibrium, and moreover the optimal control is what is usual, meaning that it's the x derivative of the value function u. And the proof, it's I mean, as I said, it's rather similar to the standard case. Given some distribution m, you fix some distribution m, you consider the optimal cost faced by a representative player, when given that all players pay according to m, and then you call this optimal cost u, and you consider the alpha star, which is the optimal control, and you call m price the distribution generated by this optimal control when all players play this. And then you consider the mapping that to each m associates m prime, and you apply a shader fixed point argument to this mapping. So it's not it's the same structure basically, and one of the main thing, but well, is like the regularity in S, but in fact the regularity in S is kind of free because of this product structure. So at the end of the day, you can get this type of existence result. Now for I think uniqueness is somehow more surprising. So as in the standard case, we need a monotonicity assumption that is written there, but somehow so in the standard case there was this monotony assumption that assure uniqueness of the solution of MFG system, and in our case it's enough to assume that the same monotonicity assumption is satisfied state by state. So for any, meaning that for any s, you have this integral between the product of mu1 minus mu2 and f of x mu1, f of x mu2, which is positive. So if you imagine that there is no s, this is just the standard monotonicity assumptions of Lasry Lyons. And under this assumption, there is uniqueness. why I say it's somehow surprising, the reason is summarized to what I was commenting on the previous MFG system. At the end of the day, what is relevant for players is not really the state. It's what they know about the state, meaning their belief about the state and their expected costs. So we may have expected that the monotonicity assumption should be stated not in terms of state, but in terms of belief about the state, which would be much less tractable and much more complicated. Actually, in the Bertucci paper, where he studies min-field game where players do not observe the initial distribution, this is exactly what is done. There is some condition that is monotonicity condition that is expressed in terms of beliefs, and expressing it state by state would not work. And the reason why it works in our case is really because of the specificity of our signaling structure. I strongly believe that it wouldn't work in more general context. So let me go through the proof. So it's a bit technical, but I will try to go rather slowly. So let me first start with the standard case. So this is a very classic proof. How do we prove uniqueness in the standard case? First, we define, okay, we have two solutions, U1, M1, U2, M2. We want to prove that they coincide. So we set U bar the difference between U1 and U2, M bar the difference between M1 and M2. And our aim will be to prove that U bar and M bar are equal to 0. And the way it's done is to compute this object. So you integral sorry, there is a mistake in my slide because it's I integrate over TD times R, but we don't have any signal, so we should not integrate over R. But so you integrate over the torus, U bar and M bar, and you derivate this function. And because U bar and M bar satisfy Fokker-Planck equation and Hamilton-Jacobi equation, you can make computation. You have relation between the derivative of U1, U2, M1, M2, and other quantities. And when you do integration by parts, you manage to prove this inequality that is written, where there is a first term that is negative. And there is a second term that implies exactly the monotonicity condition, and that we know that this term is negative. And then when you integrate over t, you integrate the derivative over t. So at the end, you will get just the difference between U bar, M bar evaluated at t and evaluated at 0. But when you evaluate U bar, M bar at 0 or t, by assumption, they coincide. So then you get that the term, the integral of M1 plus M2 times the square of the difference of the derivative is equal to 0. And then you can deduce that U1 and U2 coincide, and then that M1 and M2 coincide. So this is basically a summary of what is usually done in. For our case, we will do the same essentially. I mean, at least we will start the same way. So we will compute, we'll also set U bar and M bar as being U1 minus U2 and M1 minus M2. We also compute the integral of U bar M bar on the torus this time times the signal. And by doing basically the same computation, you will end up with the same inequality, except that first, so the first term is the same. The second term indeed looks like a monotonicity term, like the same term as in the monotonicity condition, and there is a third term. In fact, there are issues with the second term and the third term, because even if the second term looks like a monotonicity term, it's not exactly, because there is, as I was saying before, and as expected, what the term that appears is f tilde, not f. So it's like an integral of f with respect to the distribution of the state, but it's not f. And if we had this f instead, we could apply directly the monotonicity condition, but we don't have. And so basically, because the integral of a product is not the product of integrals necessarily, we do not into a term that appears in the monotonicity assumption. The third term, it is what it is, and we'll see what big sum of it. So what we were going to do now, in fact, is to integrate again according to the signal. So we will integrate this we'll integrate again this expression according to the S, with the goal of finding something that is similar to the monotonicity condition. And what we are going to do is that when you integrate the term that looks like a monotonicity term with respect to S, we manage to prove that it's positive. So when you have a minus in front of it, becomes negative. And the second term, it's actually equal to 0. So it's good, it disappears. The computation for the inequality and the computation for the equality of the third term are kind of similar. So I will only show how we get positivity of the first term. So in the next slide, I will just consider the monotonicity term integrated over the signals and show how we prove it to be positive. So, and this is where actually it's crucial to have this decomposition of M as a product between a term that doesn't depend on S and some terms that is just a density of some normal distribution. So let us start. So this is just the terms that we are interested in. The first step is to develop f tilde. We recall that f tilde is an expected cost, so we can write it as again as an integral. It's an integral with respect to S prime, and the density associated to this measure. Recall that given my signal Z, my belief about the state S prime is exactly the normal law centered at RT of Z and with variant sigma t square. So that's why there is this additional term phi that appears. This is just the definition of f tilde. Now, the second step is to use somehow the separation lemma. So we know that M bar is a product, so we just replace M bar by its expression. So M bar is equal to some term with phi time to bar. Okay, so now it's starting to be many terms, but luckily, what we observe is that there is this term phi 01s phi st sigma squared t of Z that we can interpret in the following. First, the state S is drawn according to the normal law of variance 1 and center at 0. And then given S, I draw some signal Z, and the law is exactly this term phi st sigma squared t. So if I put together these two steps, I naturally obtain just a process where I directly draw Z according to its distribution at time t, which is normal law centered at 0 and variant sigma squared t plus t squared. So it's just a rule of computation of normal laws. And now, basically, what's the aim of all this process? At the end, I would like to apply my monotonicity condition. So I have some term f of something depending on S prime minus f of something depending on S prime, and I would like that it be multiplied by some M bar evaluated at S prime. And so to do this, I will first somehow reverse the way things are drawn, and this is the subject of the next step. The thing is that the first term here in the integral, the phi 0 sigma squared t plus t squared, you can view it as first I draw z from the distribution I type t, and then I draw s prime conditional on z. Well, you can reverse these drawings. You can say first I draw s prime according to the normal law, and then conditional on s prime, I draw my z, and I obtain exactly the expression that that is written there. And now I'm very happy because I have a s prime. I have a phi s prime, and when I multiply my phi s prime t sigma squared t by tau bar, then I recognize m bar evaluated not at s but at s prime. And I'm very happy because then I know that I will be able to apply the monotonicity condition. And the last thing is to integrate with respect to z to obtain exactly my m bar 1 minus m bar 2, which is exactly what I want, because now this is really a monotonicity condition applied that we can apply to m bar 1 and m bar 2. And then I can apply it and deduce that this term is positive. And then once I have done that, basically I'm done, because okay, we have proved the inequality on the monotonicity term, and the second term you can do the similar computation to show that it's equal to 0. And then I can apply the same machinery as in the standard case and say that I integrate over t. I deduced that the term with dx u1 minus dx u2 is 0, and I deduce that u1 is equal to u2, m1 equal to n2, and then uniqueness is proved. So it's not extremely difficult. It's rather technical. But what I would like to emphasize is that it works because we have this very special decomposition of the measure of players as a product between some terms that describe the density of z given s. That is very simple. That is basically a density of a normal distribution. And then there is a separate term that only depends on z and not on s. And this is how we managed to do all this transformation. And it will be nice to I think so far we have not understood it completely. What are the exact conditions on the signal structure that allows to do this type of transformation? I think it would be interesting, but this is the result. So okay, I'm on time. So a few perspectives. As I said, I think this is basically a first model, and I believe there are many ways to generalize it in many directions. As was actually mentioned by Mathieu, you can try to generalize this assumption that the state is fixed. You can imagine that it can switch, and maybe the switching depends on somehow how players play. Another interesting thing would be to consider other signal distribution and try to investigate these questions that I just said. What are the specificities of the signal distribution that will allow us to write a simple monotonicity condition, and also that will allow us to write the system in a finite dimensional way, right? Because if you have a meaningful game with incomplete information, you may expect that the MFG that the system that we will write, the variable that will intervene will be the belief of players on the state. But the belief on the state is an infinite dimensional object. Here we are able to reduce it to one finite dimensional variable because of the special structure. But you may ask what happens for other types of signal distribution. And the last question that I think is very classic in game theory, but I have not seen so much in the main field game literature, is the question on how information is useful to players. Like we have assumed that the signals had some variance. What happens if you diminish this variance? So if players get a more precise signal, is it better or is it worse? And what are the conditions under which it could be better? We have not made much progress on this, but I think this type of question could be very interesting. So thank you very much for being there, and I would be happy to answer questions if you have any. Thank you.
Thank you very much, Bruno. Thanks for the nice talk. Are there more questions from the audience? I have at least one. I mean, I have several questions, but one was about something you showed, but I would like to understand a little bit better in the AJB equation. I mean, the way you obtain the PDE system. Probably it is in the paper, and I should read it. But how do you obtain the AJB equation? Is it by a classical dynamic programming? You redo the dynamic programming argument in order to find this expectation in F tilde?
Yeah, I think this is one way to do it to reduce the dynamic programming principle. Or you can just do by somehow by analogy, by saying that yeah, I mean, this is what I was trying to describe between by saying that somehow the S is a control, basically. It's you can view it as formally, you can view it as if it was a control.
Okay.
And then you write what it's a control basically that somehow that does not depend on X and Z. So when you do your dynamic programming principle, it goes out of the equation. So I don't know if it's
okay.
Yeah.
I see. So you view really S as a control, but a control chosen by the individual player, or because
Yeah, I mean,
uh-huh.
it's no, it doesn't make sense in terms of modelization, but
Okay.
in terms of formalism, it's the same type of equation.
I see. Okay.
So yeah. So it would be like as if I was imposing the player to play control S. Yeah, as if he had one single choice, which was to play S.
I see.
Yeah.
Okay. Thanks. I think there are two more questions. One, I think the first one was Alessandro. I don't know if you want to unmute yourself and ask your question.
Yes, well, first of all, thank you very much for the really interesting seminar. Mine was just a simple curiosity about possible extensions that you mentioned in the end about more general signals. And now, one thing that may naturally come to mind is if S is truly a stochastic process, say a finite state Markov chain, in order to keep the problem finite dimensional once one reduces it using nonlinear filtering. My question is, I mean, have you thought about this, and what may be the difficulties in dealing with the existence of an equilibrium treating this kind of more general situation compared with what you did, I mean, in this in the case that you treated here?
So thank you for the question. Yeah, to be honest, we have not really thought much about it, so we don't know much about the technical difficulties. I think one potential difficulty would be to investigate how this product structure of MS perdurates with the switching state, like the fact that MS can be written as a product. How does it become?
Sometimes you decouple it in terms of the Gaussian kernel, if you want, and another thing that solves Fokker-Planck equation. I mean, okay. So this is crucial in your proofs somehow.
I mean, it's if you want to obtain, if you want to say something about regularity in S, it's one useful thing. But somehow, I would be also maybe a bit worried about uniqueness, since I don't know. Yeah, it's hard to see. Yeah, but but yeah, I think it's a very good extension.
Thank you very much.
Okay, thanks. I think there was another question by Lev. Yeah.
Okay, yes, thanks. Thank you for your talk. It was really interesting, but my question is, I think, around the same, about the same, what was the previous one. But as far as I understand, you assume that these two Brownian motions are uncorrelated, and that's where is it important? That's also important to factorize the solution, or What for?
So you mean the Bernard motions?
As far as I understand, yes, that you assume that these two are independent ones.
Yeah.
I mean, and where is it important?
That's a good question. Let me
what's-
maybe think.
Because definitely it will be more useful to assume that, I mean, partially for financial applications, because when you optimize portfolio, it's better to base on the observations of the process, which is strongly correlated with one that you used to hedge or something. And it's very interesting. Where did you use it?
I mean, in financial application, I would be like the information I get would depend of the composition of my portfolio. That's what you mean, somehow.
No, I mean the source of randomness could be correlated. Like, for example, the behavior of your portfolio depends on the behavior of stock. And hence, if you would like to optimize something looking based on the signal
right.
process
Okay, I see.
Z.
Yeah, I see. No, that's a good question. Do we need?
Because I'm sorry for this hypothesis, but further you use factorization, and you also use some Fubini type arguments, but I'm not sure.
Yes. No. But then if the position depends, and the problem is that if the burdens are correlated, this means that by observing my own position, I would learn something about the state. No? And then I guess it completely changes everything in terms of what you learn from the state, right? So you see what I mean? I think I think this whole thing about the fact that at the end your Z is a sufficient statistic, I think it all collapses because then you observe your position and you deduce something about the state. So.
Okay, yes, that's quite that's quite clear because because it will not be so easy if you this conditional expectations will not be so clear.
Yeah.
Definitely. Okay, yes. Thanks. It was okay, yes.
I think I think it's a great question. Thank you.
Thank you.
Yeah, I guess one extreme case would be if B is even equal to B prime, then somehow as you were saying, by observing your state, by observing your X, you already learn a lot about, could potentially learn a lot about X. Okay.
Yeah, exactly.
Okay, well, there are no further questions. Thank you again, Bruno, for the very nice talk.
Thank you all for your questions, and thank you, Mathieu.